We're going to do problems 8 and 10 in section 2.2 in this video. These were the ones that were assigned for your homework in chapter 2.2, and you will see problems similar to this on our first exam and possibly on the final. So problem 8 is discovering Fibonacci relationships. And by the way, if you go online and Google Fibonacci relationships, you'll see hundreds of them online. By experimenting with numerous examples in search of a pattern, determine a simple formula for the n plus first Fibonacci squared minus f sub n minus 1 squared. That is a formula for the difference of the squares of two Fibonacci numbers. So the first thing I should do is write down the Fibonacci numbers and come up with some examples, like they asked us to. Examples of that formula with given values of n, and see if we can find a pattern. Okay, so I wrote down the first few Fibonacci numbers, and of course this is when n equals 1, n equals 2, n equals 3, the third Fibonacci, n equals 4, f sub 4, n equals 5, the fifth Fibonacci, n equals 6, f6 equals 8, f6 equals 8. Get the notation very clear. So this is a list of f sub n for n equals 1 through, well, it looks like n equals 1 through 10. So let's start out and write, looking for a pattern. We want a pattern. We want to plug in some values of n here and see what we can see. So let's let n be 2. It's kind of good to start with n equals 2 because look, we have n minus 1 here, and if we started with n equals 1, you'd have f sub 0. Well, there wasn't a 0th Fibonacci, so let's start with a bigger number. If n is equal to 2, then f sub n plus 1 is f3, and we're going to square that and subtract f sub, well, n is 2, so n minus 1 is 1, f1 squared. Now we go to our list and we see f3 is 2, so we have 2 squared, and the first Fibonacci is 1, and we have 4 minus 1 is 3. Now just keep going. We're looking for a pattern. You need to do at least 4 or 5 of these. If n is 3, then that formula up here is f4 squared minus n minus 1 would give me f2 squared. And f4 is 3. 3 squared minus f2, the second Fibonacci, is 1. Square it, and we have 9 minus 1, or 8. If n is equal to 4, we're not ready to find a pattern yet. f5 squared minus f3 squared. Plugging in the value of n, 4, and getting n plus 1 and n minus 1 for our subscripts. So the fifth Fibonacci is 5. This is 5 squared. The third Fibonacci is 2. 2 squared, 25 minus 4 is 21. Let's do one more. n equals 5. We have f6 squared minus f5 minus 1, 4 squared. The sixth Fibonacci is 8, so we have 8 squared minus the fourth Fibonacci is 3, 3 squared. So we have 64 minus 9 would be 55. Feel free to use your calculator so that you don't make little mistakes, because if you do make a little mistake, let's say we came up with 54 there, then you'd miss the pattern. So it's important to do the calculations carefully. All right, well, let's see if we can see something here. I notice that 3, 8, 21, and 55 are Fibonaccis. And most of you who did this also saw they were Fibonaccis, and some of you said, oh, it's every other Fibonacci, which is true. And that's worth credit on the problem, but it doesn't give you the formula. Remember, we are looking for a general formula for f sub n plus 1 squared minus f sub n minus 1 squared, that will be true for any value of n? Well, look at F3. It's a Fibonacci. Which one is it? Well, it's F4. So let's note that. 8 is F6, counting over. 21 is F8. And 55 is F10. And I look back and I say, well, this was when n was 2. This was when n was 3. This is what I got when I plugged in 4. And this is what I got when I plugged in 5. Now notice, 2, 4. N equals 3, F6. N equals 4, F8. And n equals 5, F10. Now I know right now that if I asked any of you, what will we get when n is equal to, let's say 7, you'll tell me we're going to get F14. So you see the pattern, I bet, right now. You see that we are doubling n to get the subscript for the Fibonacci. And that's exactly right. We're going to get, our formula becomes F, we get a Fibonacci. Which one? The 2nth. Or some of you wrote n plus n. That's fine too. Some of you wrote n plus 1 minus plus n minus 1. Well, that's 2n also, so it's fine. Some of you notice that you add these two to get 4. You add these two to get 6. And so you wrote f sub n plus 1 plus n minus 1. Well, that's equal to f sub 2n. So they're both correct answers. Question 10, you had to read very, very slowly. It had 3 parts to it, so you have to be careful in your reading and make sure that you understand each word. Suppose we build a sequence of numbers using the method of adding the previous two to build the next one, just like in the Fibonacci, so that should ring a bell. This time, however, suppose our first two numbers are 2 and 1. Oh, all right, well, let's write, take white, 2, 1. Well, we're going to add to get the next, so it'll be 3. Add to get the next, 4. Add to get the next, and so on. So we get 18 and 29, and I'm not going to do the first 15. You go ahead and use your calculator and get the first 15 terms. This sequence is called the Lucas sequence. It's just like the Fibonacci, but since we started with 2 different numbers, 2, 1, in other words, our first our first Lucas number, L1, was 2, and L2, our second Lucas number, is 1, we get different numbers in the sequence, but the generating process is exactly the same. So here is more than the first 15 Lucas numbers. And I used my calculator to add up the bigger numbers. Not that we can't do it in our head, but we just want to be really careful or we won't get the right patterns when we use them. Compute the quotients. So if any of you don't know what quotient means, then Google it, find out. Compute the quotients of consecutive terms. That means terms right next to each other. Of the Lucas sequence, as we did with the Fibonacci's. Oh, all right, well, you have to look back either to the lecture notes that we took a week ago today, or you can look in the book and see that what he did was divide f sub n plus 1 by f sub n. It's important. You're going to divide each Fibonacci number or Lucas number by the one before it. What number do these quotients approach? Well, let's just start. I guess at first you would just start out with, like we did, exactly like he does in the book and we did in class. You would take 1 over 2 and get 0.5. And then you would take 3 over 1 and get 3.0. And then you would divide 4 by 3 and get 1.333, repeating. Nothing looks interesting. 7 divided by 4, you would get a decimal. I'll fill those in a sec. I don't want to use my calculator while I'm doing the video. And then we would divide 11 by 7 and get a decimal. And 18 by 11, I'll fill those in a second. We're going to need 29 over 18 and 47 over 29 and 76 over 47 and so on. But let's divide these out and see if we see a pattern. So I'm going to put this on pause and fill in those numbers for you. Okay, so I used my calculator and put in these decimal numbers. Notice that nothing looks familiar in the first few calculations, but after 18 divided by 11, we have 1.6 something. After 29 divided by 18, we have 1.61. And now look, 76 over 47. It looks to me like this is approaching phi. Now if you don't know what phi is, you need to know the first 4 or 5 digits of its decimal expansion, and you need to know its exact value, 1 plus the square root of 5 over 2. Now it seems that way. Well, how could I check? It's not really conclusive. I'm going to just go up and skip a few steps here and take these the furthest out I went. Let's see, which Lucas numbers are those? We have 3, 6, 9, 10, 11, 12, 13, 14, 15. Okay, so if we take Lucas 15 divided by Lucas 14, we have 843, 843, the larger one, divided by the one before it, 521. And we get 1.61804. 1.61804. And phi, this is correct out to 4 digits to phi. So we can feel sure that the ratio of a Lucas number to the one before it, as you go further out in the sequence of Lucas numbers, those ratios become closer and closer to the number phi that we derived exactly last Monday's lecture when we looked at the fractions with all the ones in them. That video is called The Hunt for Phi. So what we have so far, what you would write before we answer this last part, you would write on your paper something like this. As n gets big, or you could just say as we go further out in the sequence, the ratio of a Lucas number to the one before it approaches, I would put arrow phi, or you could put is approximately phi. None of them are equal to phi. And let's review what phi is, just because I'm sure that it's easy for you to forget this. What is phi? Well, phi is the golden number. It is equal to 1 plus the square root of 5 over 2, as you can see in the video entitled The Hunt for Phi, or read in the book. And it is approximately equal to 1.618033, and it keeps going. I'm happy if you just know that it is approximately 1.618. All right, now what's at the top of this slide is the rest of the question. Many of you didn't see that. Again, read the whole question, and at the end make sure you've answered it all. Try 2 other first terms and generate a sequence. What do the quotients approach? Well, let's do that. I'll call it T sub n for Tina's sequence. Okay, and I'm going to start with, how about 2, 3? Oh no, that would give me Fibonacci's. Let's not do that. Let's start with 2, 4. Okay, so then I'm going to have 6, 10, 16, 26, 42, 68, 110, 178, and 288, ... Generate quite a few. And now I want to know if the same thing happens. Well, I don't have to divide 4 by 2, 6 by 4, 10 by 6, because I know all I want to check is, as n gets big, do the quotients approach phi? So I'm going to go out here and just pick the last two. And I'm going to try that and see. That would be, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I'm going to try T11 divided by T10. And I get equals 288. If it doesn't look good, we'd need to go out a little further. And 288 over 178 is, let's see on my calculator, 288 divided by 178 equals, oh great, 1.61797 and more. And this, you could just say, is approximately phi, because it's, I mean, if you rounded it off, it would be 1.618. It's very close to the number. And as we go out further, it will agree with phi further and further out in its digits.